All right, here's 6-3 day 1. Important topic. For most of our probability calculations, we stay pretty much consistent with the normal distribution, but a binomial is the one time that we'll use like a different calculator feature and do calculations for like a different distribution type. Okay? So this first part is basically that if you want to model a problem with a binomial, it's got to meet 4 criteria. B, you can remember them with the acronym BINS. B stands for binary, which means every single outcome has to be labeled as success or failure. I, the trials have to be independent. N, you have a fixed number of trials. Again, we call that N. The way you should approach that is you should be able to find that number in a problem. And S stands for success. The probability of success has to be the same for every single trial. Now, before we get into any problems, I just want to run through a few of them to get you thinking about, hey, does it meet all these conditions? Okay, roll a fair die 10 times and let x, our variable, be the number of 6s that you get. Well, do I have success or failure? Well, yes, I do. You could say that for each roll you either get a 6 or you don't. So yes, it's a binary. Is each roll independent? Yes. And again, these last two, you should be able to identify these numbers. 10 is the number of trials, and the probability of what we're calling success, which is rolling a 6, is 1 out of 6. So that could be modeled with a binomial. Again, as we're going through these, that you're probably thinking that, okay, so we could, well, what does that mean? We'll get to that. Okay. Shoot a basketball 20 times from various distances in the court and let y be the number of shots made. Is it binary? Yes, it is. You can either make the shot or miss. Success is making it. Independent? Maybe, but we'll say yes. We'll say that whether you make or miss each shot isn't affected by the other. We'll make that assumption. N is 20. Now it says to move around and shoot from various spots. That actually means the probability of success is going to be changing depending on where I shoot it from. That's not going to work with a binomial. Okay? If it violates any one of these conditions, using a binomial distribution is not appropriate to do. If they stayed in one location and I had a probability for them making or missing that shot, then I'd say, okay, then we could do a binomial, but that's not what's happening. Observe the next 100 cars that go by and record their color. As that problem is written, it doesn't seem to establish what we're considering success and failure. And keep in mind with binomials, those terms sometimes get funny. Success is the event that we're measuring. It doesn't mean it's a good thing necessarily. Failure is that the event that we were trying to look for didn't occur. This problem doesn't seem to have it. Not a binomial. Shuffle a deck of cards, turn over the top, put the card back in the deck, shuffle again, repeat the process 10 times, and let X be the number of aces you observe. Is it a binary? Yes, we could say success is getting an ace, and failure is not, because you shuffled and put it back. We'll say that, yeah, we're good and we have independence. 10 trials. This one could be a little bit tricky for you. Wouldn't necessarily expect you to know it off the top of your head, but again, for S, we should be able to identify what is the probability of success, and it's 1 out of 13. This is one of them that I found to be the most interesting of all the ones I threw in your notes. Choose 3 students at random from your class and let Y be the number who are over 6 feet tall. Binary. Yes. Independence. Yeah, one person's height shouldn't affect another. Fixed number of trials. And here all of a sudden, P, the probability of success. That would be the odds that we select somebody that's over 6 feet. It raises the question for me, the sampling up here. Was it done with replacement? If it wasn't, then P is going to be constantly changing. But even as it is, without just from this description, I guess it could be a binomial, but this whole probability of success, I need that to not change from one selection to another, and I don't know what it is. So for the time being, with this kind of issue of getting a value for P, I'm just going to say no to that one. We would need a little bit more of the specifics before we could say that that's a binomial. So this one's a little crazy. Flip a coin. If it's heads, roll a 6-sided die. If it's tails, roll an 8-sided die. Repeat this process 5 times and let W be the number of 5s that you roll. Binary, absolutely. Roll a 5 or not. Based on that process, every trial seems independent. N is 5. Okay, this is just kind of an interesting one to show you. Certainly off the bat, I would not expect you to come up with this, but if you were to put together a tree diagram, you have your coin flip, and then you have 5, not 5. If you got tails, it would be 5 and not 5. The flip is 50-50, but if you got heads, the odds of getting a 5 is a 6th. Not a 5 would be 5 out of 6. 1/8 and 7/8. Now for getting a 5, you could do a half times a 6th and add that to a half times an 1/8. And you might be like, what on earth are you doing? And again, on your own, I wouldn't expect you to do this yet, but this one seems kind of deceiving, but when you get down to it, for each trial, the odds you get a 5 is like 0.146. Okay? So that one's a lot harder to see, but if you dig deep, yeah, you have a fixed probability of success. For every single trial, you have about a 14.6% chance from the beginning of the trial that you're going to get a 5. Now, after you flip the coin, those odds change. They go from 1 out of 6 to 1 out of 8. But if we include the coin flip as a part of the trial, then we could say from the beginning of each individual trial, it's about 0.146. All right, so we're going back to rolling doubles. Okay. Yeah, so the odds of rolling doubles is 1 out of 6. Okay, and we're saying that we're going to do 4. So first of all, you don't have to tip. I'll get more clear as we go on as to what you need to write out for problems like these. I'm not going to do a ton with that yet. Okay, but you should know that simply, like for the eventually we'll get really, really intensive with the calculator, but x is a binomial, n is 4, and P is a sixth. Okay? So all 4 rolls, no doubles. Okay? No doubles. This is when we wouldn't have to think about it like a binomial. If you just use the idea of a complement, you could go through and just take 5 over 6, and given we have independence, we'd raise it to the 4th power and be like, all right, 0.428. Okay? This is where things get a little bit more interesting, is if it's 1, we could say, all right, so we need 5 out of 6, and then 1 out of 6, but this needs to be the 3rd power, right? So it's like I have the first 5 over 6's, but the last one needs to be 1 out of 6 because I need to get a double, okay? But there's 4 different ways. Like what I have calculated there is just one way to get doubles. It would be on roll number 4. It could happen on roll number 3, number 2, or number 1. So that calculation needs to get multiplied by 4. I'm starting to lead you to what the binomial formula looks like. So eventually we'll do 4 choose 2. What I just got, the reason I did that for it was 4 choose 1. I had to look at the number of ways one event could happen in 4 trials. It's a really straightforward one because it's just 4. If you ever need to do it, I can show you on there's a, I mean, you may already even know where it is. There's a combinations button on the calculator. Don't bother with the formula or anything. We would just go get it from the calculator because all we want is just the number. I don't care about the math involved with the combination. You know, if you did them before, it was probably in like an Algebra 2 course or something where you did get into the ins and outs of how the formula works. We just want the answer of how many ways it can occur. So here is what your binomial probability looks like. Okay? So just to be clear here, this is not new. N is the number of trials. That should be known. P is the probability of success. And in fact, those 2 things should be clarified at the very beginning of a binomial problem. 1 minus P, we saw that already come up. That's the probability of failure. It will obviously just be the complement of the probability of success. Remember, the whole thing started with the B in bins by saying these events have to be able to be labeled as success and failure. K is the number of successes. Okay, so on the one that we just did, we had said that K was 1. This is just kind of a shorthand way to say 4 choose 1. And then I had said probability of success was a 6th. And I was talking about one of those. Failure was 5 over 6. And we were talking about 3 of those. So we've already seen that formula in action one time, but that is the basics of how it works. All right, so we have already clarified that this, I mean, that's where, again, the process should start. You think through bins, and you're like, okay, this is a binomial. There's 3 things you should do prior to any work that you write out, that you would say X follows a binomial distribution. In this case, N is 4, P is a 6th. Okay? I've already written that once, so I'm not going to write it again. So this is now saying 2. So we have to look at the 4 trials, see how many ways could 2 successes happen. Success is looking for doubles. I want 2 of those. Failure is not, and I want 2 of those. Okay? Now there's already a calculator tutorial posted. To actually get this answer, that is the feature you're looking for. This is a binomial PDF. It's a fairly simple feature. You just have to enter in all the info that you have. Like the calculator just needs to know N and P and K and all that stuff, and it'll do the number crunching. So on part B, this will also be a calculator thing, but I want to contrast that with the first part. This is binomial CDF, because here's what's going to happen, is this wants the probability that I get doubles 3 or more times. Okay? So I'd have a binomial PDF for 3 successes. And I'd have to do another binomial PDF for 4. And this doesn't seem all that bad, but what if we had one where it was like, 20 different ones we had to add up? That wouldn't be good. The CDF case takes care of that. Okay? But you'll see the binomial CDF can only do less than. So what I would have to tell it is I'd switch it to a complement and say the probability that I get 2 successes or fewer, or get doubles twice, once, or not get them at all, and subtract that from 0. That number the calculator can get. Okay, so if you have a greater than, and you're going to use the CDF feature, you have to switch it to a less than or equal to. Okay? Comes up all the time with the CDF. So the question was asking, so that 0.016, that's coming from the binomial CDF feature. Would you be surprised if this occurred? Yeah. This probability is quite low. Right? If you rolled 4 times to get doubles 3 of the 4 or 4 out of 4, it would only happen about 1.6% of the time. All right, switch the context down here. To show that the situation is a binomial, I'd think through bins. For each question you can guess right or not. If you are guessing, it seems like a safe bet that each guess is independent. And then, for n, all you need to do there is just identify the numbers. There's 10 questions, and then p, a fixed probability of success, is 1 out of 5. Okay? So x equals 3. This is an exact number of successes, so you would go binomial PDF. N is 10, P is a fifth, K is 3. Okay? What it's going to calculate for you is this. How many different ways you could get 3 questions right. We need 3 correct answers. We need 7 wrong guesses. And then this 0.201 would come from the calculator. Probability, and it seems like it's actually quite high, of guessing 3 questions right is 0.201. Probability that you would get a passing score. Okay, by the way, if you want to put this into your notes, that's a binomial PDF. This is going to use the CDF, right? The CDF case has multiple scenarios that we're going to account for. What are the odds that we would pass? You got to get 6 or more right to pass the quiz. What are the odds we pass? Well, that would be getting 6, 7, 8, 9, or 10. Okay. So I'm looking at the probability that x is greater than or equal to 6, but remember, I immediately want to switch that because the calculator can get less than or equal to 5, right? The odds that basically, I mean, this one is nice because you can put it in really simple terms. I'm looking for the odds that we pass if we're guessing. The calculator can get the odds that we fail, which is fine because they're complements. I just got to subtract it from 1. 0.9936 is the number the calculator will spit back to us. Subtract it from 1. 0.006. Would you be surprised if Patty gets a passing score? Yes. I absolutely would. The odds of her passing this quiz, 10 questions, multiple choice, 5 possible answers, the odds that you would pass it from guessing are very, very low.